having me here and giving me this chance to share this work in progress. You've already seen this talk a few weeks ago, but for those who have not, I guess there'll be something interesting for you. So this is basically work done by Yannick, who's going to finish his PhD towards the end of this year. And we hope to sort of like submit this sometime next month. And we've developed, so Yannick has developed a purely deep learning model for El Nino, La Nina forecasting during his PhD. And what we try to sort of focus on is that what sets our model apart is that it's well calibrated. Just to explain this, it's a fairly easy notion that our model, along with the prediction, it also gives a kind of a uncertainty estimate on the prediction, how sure it is that this is the prediction, right? And when you have an uncertainty estimate given by a model, you can say like, oh, I'm 50% sure that this is going to be the case. And then you can also evaluate the actual error from your prediction. So ideally, a calibrated model is one where the more you're unsure, your actual error is also large. And the less you're unsure, the more sure you are, your actual error should also be. Because if it's the other way around, then something is off, really off, right? So you don't want to have an uncalibrated model. So our model is well calibrated, and sort of we make some design choices to ensure this. And what I also like to say is basically, this is yet another deep learning ENSO model. And in this talk, what I'm going to do is in the beginning, just so that we are all on the same page, I'm going to talk a little bit about the ENSO, which is the El Nino Southern Oscillation. I'm not going to talk too much about what is deep learning, but then I'm of course going to show you the model architecture and the thoughts that went behind in designing the model architecture and the training of the model, right? Okay, so let's get started. So what is the ENSO? The ENSO is essentially a oscillating phenomenon of a weather state in the tropical Pacific Ocean. Okay, it manifests itself in the surface ocean temperatures as well as the subsurface ocean temperatures. And that's what's shown here in this graphic. So we can basically, let's start at this subpanel C. That's the onset of an El Nino event, which starts by some abnormally warm temperature. So red essentially means abnormally warm, and blue means abnormally cold. It starts by abnormally warm temperatures gathering up in the subsurface levels in the equatorial Pacific. And then some other things go on, atmospheric forcing, some stochastic forcing happens, and that sort of amplifies this. So there are some feedbacks loop involved that amplify this abnormal tendency to become abnormally warm. And then you start seeing this red band on the surface of the ocean. And that sort of amplifies even more. And then you have this mature El Nino. So a mature El Nino is basically you have a band of red abnormally warm temperatures in the equatorial Pacific, okay? And this already takes like 6 to 9 months to develop, yes. These are westerly wind events. So it's winds which are blowing from the west along the surface of the ocean, right? And they are rather stochastic. So that's somehow, and that's the atmosphere, although El Nino is fundamentally an ocean phenomena. So you say that the atmosphere is then stochastically forcing this system, all right? And this takes like around 6 to 9 months to develop from like C, D to E. And similarly, like again, it takes a few months to sort of like, another 6 to 9 months for that to sort of decay. So it reaches the mature El Nino phase, everything becomes very warm, and then sort of the temperature slowly sort of, subside. It loses its abnormality. And then typically what happens is you enter into the La Nina phase that, the opposite begins to happen. Abnormally cold temperatures develop in this subsurface Pacific, and that sort of leads to the full mature La Nina phase. And then this cycle sort of repeats itself. So it's an oscillation, but it's spatio-temporally spread. And the oscillation is not really exactly precisely periodic. You know that it oscillates, you know that it's going to repeat itself, but you don't know precisely when. And that is sort of the challenge in predicting the El Nino, right? So that's the challenge in predicting the El Nino or understanding it as a system for its own sake. But why do we really care? So I really like this picture of our globe, so to speak. if you see, this is the United States on the top right, and then this is basically the Pacific Ocean, and you have Australia on the bottom left. And this is like one cross section of like one half of the globe, right? And most of it, like 90% of it's just the Pacific Ocean. And when we say that, this band in the Central Pacific is abnormally warm, I mean, you're talking about a huge, huge area of the surface of the Earth that has suddenly become warm, right? Or suddenly become cold. And that is bound to sort of like, influence what's going on in the atmosphere, what's going on in other parts of the ocean, right? And this is why we care about the ENSO, because this is such a huge thing, the Pacific. Um, Abnormal events in the Pacific are known to sort of lead to extreme weather patterns all around the globe. And these are what are called El Nino and La Nina teleconnections. That's typically shown in these kind of schematic cartoons. So these are teleconnection impacts of El Ninos, where you see, like, in the one point which I did not mention is that typically the mature phase of the El Nino or the La Nina actually happens in winter, DJF months, December, January, February. And when you have the mature El Nino, then you have wet and warm conditions in the Pacific, abnormally warm conditions, let's say over South Asia, wet and cool conditions over Florida, wet conditions over California. And in the following, when you have El Nino-like conditions and in the summer, then you have dry conditions over the Indian subcontinent, dry conditions over the maritime continent, over Australia, and so on, right? And for the La Nina, when you have abnormally cold temperatures, the opposite tends to happen. I mean, it's not literally an exact opposite, because the extent and the shape and the magnitude of the two warming and the cooling are not really symmetric. There's some asymmetry involved. But as a general rule of thumb, you can expect, places which tend to have extremely dry weather conditions during an El Nino will tend to have extremely wet weather conditions for a La Nina, and sort of this and the other way around, right? So El Nino and La Nina's impact, so the bottom line here is that El Nino and La Nina impacts extreme weather events, leads to extreme weather events all around the globe, yes. El Nino, La Nina. Yeah. Yes. They don't. So what you would do is, let's say we have 50 years of weather data from reanalysis or whatever, and we have around, let's say, 5 El Nino events in these 50 years, right? We extract those 5 DJF months, the data for those 5 DJF months, and average them to make this picture. And similarly, we would have maybe 6 or 7 La Nina events, and those are separate winters. And you can create a separate average for that. That is how these kind of teleconnections are talked about. All right, and it's another thing is that, like, it's also very challenging to predict El Ninos because of the spatiotemporal complexity involved. And this is one sort of like a anecdotal example of this sort of and this El Nino that was supposed to come in the winter of 2014, because in early 2014. You see here on the right, these are models that predict the El Nino. And when these models were initialized in April 2014, all of them were showing that, like, we are going to head towards abnormally warm temperatures. But when you actually sort of revised the prediction in October, it did not turn out to be that case, right? So something happened in the spring and summer of that year that sort of went counter to what the models were expecting. And in fact, there was a lot of buzz in the spring of that year that we are heading towards like a really big El Nino year, but that did not happen. And it actually happened a year later. And that caused a kind of a pause between the community which tries to model El Nino, because before that there was a kind of a general consensus that we're almost there. Like, we have fairly good climate models of different levels of complexity, and they do a fairly good job of predicting El Nino and La Ninas, at least like 6 to 9 months in advance. But this case sort of like, threw everyone a little bit off balance. And then in hindsight, there were a lot of discussions on what went wrong, and westerly wind events, the stochastic forcing was one of the things that we found, like, that the models were not getting right. But bottom line here is that, like, it's challenging to predict DL ENSOs, right? And that is where, let's say, now deep learning models come into the picture, right? So they said, okay, we have already physics-based models. There are also several statistical models. So here, for example, on the right, if you see these two groups of models, on the top are the actual physics-based climate models, and on the bottom are like around 8 to 10 statistical models, not deep learning, but statistical models of the ENSO, right? So they come in different flavors. So for example, this one model called the CDC LIM, so linear inverse model. If you've heard of Koopman operators, so LIM is something like, Koopman operators borrowed by the climate community and renaming it slightly and so. The statistical models are stochastic models. At least I know for the LIM that is the case. And in this list, actually, to be honest, there's one model from Russia, which is actually a neural network based model. This one, UBC NNet. That's from a group in Russia. That's a neural network model. No, I don't think anybody uses Brownian motion, but yeah, maybe. They're mostly discrete time models. I'm familiar mainly with this neural net model and the LIM model. Yeah. Right. So you have physics-based models, you have statistical models, and then let's have deep learning models as well. And this was, I think, the first high-profile paper which actually sort of came up with an ENSO prediction setup. And here, basically, what they did was they predicted what is called a Nino 3.4 index, a Nino index. The Nino index is essentially one scalar number per month. Okay, per month you have one scalar number, which is an average of the temperatures in somewhere in the Central Pacific. And that number sort of tells us if that number is high, that it means it's an El Nino kind of situation. If that number is negative and high magnitude, then it's a La Nina kind of a situation. And this setup that Ham et al. Gave tries to take spatiotemporal data, but predict the Nino index. And if you look at it carefully, it's set up more or less like a one of these classical cat-dog classification kind of a thing, right? Like you have these images. Of course, now you have multiple images, but you go through multiple alternating convolution and max pooling layers, and you compress the data, and finally you have a fully connected layer, like a MLP kind of a layer. Yeah, so the input images here are sea surface temperature, SST, and heat content, upper ocean heat content. And these are also snapshots at 3 time steps. So heat content for 3 time steps at T0, T-1, and T2. SST similarly at 3 time steps, T0, T-1, and T2. So essentially 6 snapshots. 3 months. So the El Nino problem, the task is you have monthly data and you predict monthly dynamics. Yeah. Yeah. Yeah, so you typically talk about temperature anomalies. So the deviations of the temperature from the climatological average. That plus minus 3 is already like, you are beyond 1 sigma. So most of the data is between like minus 1.5 and plus 1.5 in most places. Yeah. 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 And that's a really bad event. Yeah. 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 And the average temperatures in the Pacific are somewhere between 27 to 30 degrees. So, and that's the baseline against which we have this anomaly. Not, I don't know so much about the biodiversity, but I think El Niños would. Yeah, that's true. Um, this particular fish kind of a phenomenon has also to do with the upwelling here, because in an El Nino, this upwelling sort of like, weakens. And cold waters from the bottom do not rise up. And it's in the normal year, when you have this kind of overturning thing, like cold waters rise up off the coast of Peru, that they bring in a lot of nutrients from the bottom of the ocean. And that sort of has repercussions along the food chain, if I'm not so wrong. That's one example, but I'm pretty sure maybe El Nino events also have impact on environmental situations, like, because it can lead to extreme heat over Central Asia. So vegetation might take a hit, but I'm not an expert on it. So yeah, I mean, I don't really know if there is a actual like original cause for the El Nino. Like, I don't think there's a consensus also. Yeah. Yeah. But the cause and effect between the ENSO system and these other downstream events, like, wildfires, heat waves, monsoon droughts, that's pretty causal. I think that's understood. Yes.
For India, for example, is there like a study which over decades and decades of like data that we have studies like which teleconnections impact like the monsoons in India the most? For example, if something in the Pacific happens year over year over year, and it leads to something specific in India in the monsoons. So is there any study that does that for India or some other region? Like some particular teleconnection and mostly a lot of times causes something specific like a weather pattern or climate pattern to happen in a particular region. So is there something like that for India?
Yeah. I mean, so it is well known that the ENSO system uh, impacts the Indian monsoon, especially over central India. Um, and there are like a lot of studies that try to understand this relation, and it's not so simple. But on a macro scale, the general rule of thumb is that an El Nino events are more likely to be correlated to drought-like conditions, and La Nina events are more likely to be correlated to wetter than normal years. But this is not a sure shot thing. This is not a sure shot.
And a kind of follow up. So these teleconnections that are there, the time scale of these, are they for a period of few weeks, a few months? Like, what is the time scale? Like short, medium, or long term? Like, what they impact more?
So Professor Partha might sort of maybe, I don't know, say if I'm correct or not, but my understanding is that, like, that El Nino conditions, because El Nino is a slow moving system, takes 6 to 9 months to develop and another maybe 6 to 9 months to sort of decay. So that provides a kind of a background condition for the monsoon season, right? So like monsoon season starts in June, ends in September. During that time, there is not going to be a drastic change in what is going on in the Pacific. It's probably already entered into an El Nino or developing El Nino, but there's nothing drastic going to happen on the timescale of a few weeks or so on. But what is going on in the Pacific on that slow timescale provides a background forcing, which is, let's say, very different for a monsoon year where the opposite was happening, where a La Nina was background. So that is how the relation is. Like, El Nino is a slower moving dynamics, provides a background, and monsoon is like a much faster dynamics, but it reacts differently to the different backgrounds. Right? Okay. All right, so this was the first model. What I want to sort of drive home, this was 2019. It's actually a fairly simple model, so to speak. Like, you could probably like code it up very fast, few convolutional layers and max pooling layers, and then you're spitting out essentially one scalar. Not one scalar actually, 23 scalars, because it's trying to predict 24 months in advance, but one scalar per month, right? And then already that, it showed a lot of success over the traditional models. So here you have something called correlation scale. So correlation scale essentially is that if you have spitted out the Nino forecast index for a particular lead time in the future, you have the model forecast and the observed forecast, and you take the correlation between them. And the orange line is the Ham et al. Model, and it manages to have a high correlation scale. And rule of thumb is that, if you have a correlation scale higher than 0.5, it's a good model that can be relied upon. So it maintains to be above 0.5 almost up till 17 months, right? Which is much better than the existing models at that point. And on the bottom panels, it's sort of trying to analyze this correlation scale depending on when you initialize the forecast, but we won't get into that right now. And then, cut to 4 years later in 2023, we have this huge transformer-based model by Zhu and Zhang. And that's sort of set up in this typical, almost, for those of you who are familiar with like the GPT architecture, it's like this typical encoder, decoder kind of an setup. And then they use something called a time embedding, which was somehow kind of a new novelty as opposed to just having position embedding. And in this, the advances over Ham et al. Was that they took in these snapshots as input, but they were also outputting snapshots. It's no more a scalar value of the Nino index. They were actually predicting the SST fields. The data is also slightly different. So Ham et al. Was using sea surface temperature and heat content. But what these people did was they took sea surface temperature and actually ocean temperature at 7 different levels below the ocean as well. So 7 levels and then 9 months into the past. So that's the thing. So this is something that I sort of did not touch upon, but I wanted to say, I have this here on this slide. So typically what you would do is, because El Nino and La Niñas come in very rarely, so in the actual observation reanalysis data period, you probably have just like 5, 6 El Ninos, 6, 7 La Niñas, not much to train upon. So what people have established almost like a convention now is that you do pre-training on CMIP data. So Ham et al. Took model output from 21 CMIP5 models. Zhu and Zhang took 23 CMIP6 models. So you and that is a lot of data, because there you have thousands of years of data with hundreds and thousands of different El Ninos and La Niñas, right? You pre-train on that, and then you fine-tune on a small subset of the reanalysis data. And then you can issue predictions for the rest of the reanalysis period. So that is the standard setup. So we don't have to do that, right? Because the CMIP6 model data is already out there. We just need to download it. We just need to download the CMIP6 data and train our model on that. Yeah. And here are the results of the Zhu and Zhang paper. So here, for example, they show the correlation scale of the Nino 3 index, and compares it to the CNN model. The CNN model is like a stand-in for the Ham et al. Model. And in terms of the Nino 3 index, they are more or less equally high performing. They have similar correlation skill up to 17 months and so on. But of course, I mean, the geoformer model gives you much more than the Nino 3.4 index. In fact, the Nino 3.4 index is something that it was not trained to do well at all. It just comes out as a statistic out of its model forecasts, right? Whereas the Ham et al. Really trained to be good at the Nino 3.4 index. And then they also compare their skill to these other physics-based models. In particular, they take something called the NMME. It's North American Multimodal Model Ensemble. It's a group of models that are typically used to sort of like, to study the ENSO, for example. And then you have here the red line, which is the correlation skill of the Zhu and Zhang model, the geoformer model, they call it, the geoformer model, which is like doing way, way better than the physics-based model. The correlation skill is up to 17 months, whereas the best performing model from like the GEM NEMO has a correlation skill up to only 10 months, right? So this is sort of the background for what kind of models exist for the ENSO. Deep learning model exists for the ENSO, and the task, as I said, it's monthly data, and then you also predict monthly data, predict monthly dynamics. In the case of Ham et al., it's a scalar value up to 24 months. In the geoformer, it's all input fields up to 20 months. And then in our contribution in this yet another ENSO model, what we want to sort of improve upon is that we wanted to develop a model that was probabilistic, so that we don't have to train the RMSE loss anymore, because the root mean squared error loss is known to sort of lead to blurry outputs. And the geoformer model or the hum model, neither of them are probabilistic. And we also did not want our model to be too task specific. Like, we wanted our model to sort of have a little bit of generalizability, a little bit along the lines of a foundation model. And as the title says, we want our model to be well calibrated. And in addition, we also wanted it to be scalable to larger input time steps, more variables, and so on. And for that, these are the sort of improvements that we include. We use the continuous rank probability score to train our model. We use self-supervised learning via masked tokens. So this is something called masked auto-encoding, which is a standard way of doing self-supervised learning for visions in vision tasks. And we achieve well calibrations by changing our masking strategies during this SSL step. And the scalability we achieve by sort of including a kind of a transformer block called the perceiver, where you can essentially map your input data, high dimensional input data, to a low dimensional latent space, and then work with the latent space onwards. Masked autoencoding, let me just quickly explain masked autoencoding, what that is. A typical autoencoder is something where you have an input image, you have a kind of a bottleneck, you compress your input image, and then you sort of decompress your input image to reconstruct the input image. And the task is that, like, you should be able to get back your input image in spite of having an information bottleneck in between. Masked autoencoding changes this paradigm slightly, and it says that, like, I don't care about the bottleneck, but what I'm going to do is I'm going to sort of corrupt my input image. I'm going to sort of delete pixels in my input image, and my neural network has to recreate my image, even though sometimes 90% of the pixels are deleted, right? And still you manage to sort of recreate the input image. And in doing this over like hundreds of thousands of samples, the hope is that the neural network learns something useful about the structure, the spatiotemporal correlations of your data. And we apply that to this ENSO task. Our data input variables are same as geoformer, monthly snapshots of subsurface temperature and surface temperatures, and actually also 2 times winds. And we take a 36 time step window block where for forecasting, we forecast 28 months, and 8 of those time steps are our input. So we have a context of the last 8 months, and we want to forecast around 2 years, 2.5 years into the future. And this would be our input data blocks. Like, you have lat, long, and time, and then you have variables, let's say C1 to C9. And we don't take the CMIP6, all of them, but we consider on one particular model of the CMIP6, the CSM2, and especially this variant called the large ensemble run of the CSM2. And then we take the pi control for that in special, which is basically does not have climate forcing, anthropogenic climate forcing in that. And for the real world validation, we use something called the GODAS surface ocean reanalysis. And our structure of the model is a little bit like this. So we have our input, and then we have something called the modality encoder, which basically would mean that, you take the input, and if you have wind, it encodes the wind in a slightly different way as opposed to, let's say, temperature. And if it's subsurface temperature, it also encodes it a slightly different way. And then we have the perceiver block, which allows us to sort of, reduce the dimensionality of our model. So in this perceiver block, basically we have the latents, and then our input may be high dimensional, let's say 100,000 dimensional, and then we might say that, oh, we just want like a 1,000 dimensional latent space. So our 100,000 dimensional input from the modality encoder gets mapped onto a 1,000 dimensional latent space. And then from then on, in this actual transformer block, the data that is being processed is 1,000 dimensional. So then the actual dynamics that is being understood, or the actual spatiotemporal correlations that we are trying to learn using the masking, that is being done in a much more lower dimensional space. And that makes actually the model very more scalable, because it somehow becomes independent of what kind of high dimensionality data you provide. Like, you might increase your sort of data dimensionality from 1 degree to now 0.25 degree, but we still map it to a 1,000 dimensional latent space, and our model somehow does not really care. It scales with the data size. And once we've processed it, we sort of have to have another perceiver block which sort of remaps it back to the high dimensional data space. And in the end, we have something called tail networks. And this is, it's a kind of a hackish trick to create a kind of a pseudo ensemble. So our model is inherently deterministic, but having a bunch of tail networks basically says that, like, give me a set of possible outcomes and not just one snapshot. Give me a set of possible outcomes from this one latent space that I have at the end of this perceiver block. And we use an ensemble size of, like, I think it was 8 at one point and also 17 at one point. And you having this now ensemble, so if we have ensemble size of 17, then there will be 17 tail networks, each of them responsible for one member of the ensemble. And when we have the ensemble, we can use the continuous rank probability score to sort of train our model based on that loss. And these are our results. So this is basically just what is called a zero-shot forecast. So this involves no fine-tuning. We just trained our model on the CESM2 PyControl run we had, like, I don't know, 10,000 years of data. And then we straight away said, okay, now here's the reanalysis initial state for the GODAS data set. Give me the predictions. And these are sort of, what was it? At a lead time of 12 months. So all the orange bars, it looks not look orange in the slide. So the error bars, the reddish error bars are from our model ensemble, and the target is given in blue, right? And it looks pretty good. And this is like a 1 year ahead forecast from 1980 to 2000. And not just that, our model is also, this slide basically tries to communicate that our model is also very well calibrated. This is something called a rank histogram. What means is that we have an ensemble size of 9. So we have 9 ensemble members. And here, if all the 9 histograms were to be at the same level, and the different colors are just different lags, so you can just focus on one color, let's say the lightest green. So you have 9 times these light green bars. And if they were all at the same level, it means that, they managed to capture all the data all the time, right? And that would have been the dashed red line. And for most of our, so the message from this plot is that for most of our ensemble members, we are very close to the red dashed line, and that means that we have a very well calibrated model on our hands. And this is just, I think this is a last result. This is to give you a qualitative flavor for what kind of the fields look like that are outputted from our model. On the left, you have ensemble mean, and on the right, you have targets. For 2 forecasts, the top one is at 6 months lead time, and the bottom one is at 18 months lead time. And although, I mean, the ensemble mean is fairly blurred out and does not have these finer scale features, overall, it gets the broad pattern correct. If we come back to the correlation scale that we looked at before with the geoformer and the Hammett-All model, right? So here you have the geoformer correlation scale in orange, and our model correlation scale in green. And you see that, like, we slightly overperform the geoformer, not by a big amount, but slightly we do better. But then our point is also not just to be overperforming the geoformer for performance's sake. The point is that we have an almost as good, if not better, model than the geoperformer at low compute efficiency, and at the same time, which is probabilistic and well calibrated, right? This is something that we do. Basically, when we mask the input data to do this self-supervised learning, we have different choices of how do you want to mask. And we found that, you could mask out one patch, or you could mask out, because our data is like 3D volumes, you could mask out like these kind of tubes, or you could just use random masking. So we found that different choices of masking have different impacts on your final model. In the end, we ended up choosing something called a time-weighted mask. That's the blue bars. The blue bars is something called a time-weighted mask, and that is that basically gave us the best results in terms of correlation skills. It gave us, in fact, even better results than what would be a prediction mask. A prediction mask would be like, just always mask out the last part of the data and ask the model to recreate the last part of the data based on the previous part of it. I mean, that would be that's basically the task that we want to do, right? But it turns out that if you do that naively, if you just say that, like, even in my self-supervised learning step, I will just ask it to do the prediction task, and then you will not get this zero shot forecast generalizability. Then it sort of tends to overfit too much to your training data. So in terms of this generalizability and having good calibration, we found this time-weighted thing was a good choice. It's a time-weighted mask. So essentially, because you have these data cubes, right, lat, long, and time, and the masking has a kind of a time information. Like, you do not mask all time points, all time slices with the same probability. You sort of keep changing the probabilities a little bit. Yeah, and that's filling the gaps is like the whole task of masked auto-encoding. You mask out, and the new network has to fill in the gaps. So we do that after training. After training, we say, like, because once the network knows that, okay, I need to fill in the masks, and you do that. So once the training is done, you can take the test data set and say, now the mask is just the second half of the data set. That becomes a prediction task. Like, the prediction task is a subtask of the overall masking task. So that is how you. Yeah, yeah. So that's basically the general idea of masked auto-encoding. Where is tau x and tau I here? Oh yeah, these are the wind stress. These are the wind stress. That's the worst variables to predict, basically. Yeah, which is understandable. I mean, they're quite stochastic. Over the entire, so we take a much larger area. We take the SST fields, like the whole data. We take, I think, like, I don't remember exactly, but yeah. So 20 degrees north to 20 degrees south, and the wind stress is 10-meter winds. 10-meter winds. Yes. Yeah. So so the thing is, and we did some ablations as this as well. You're absolutely right. So in this setup, in this monthly data kind of a setup, like, having tau x or tau I actually does not really make much of a difference. Yeah, it does not actually make much of a difference. We realize that in hindsight, and it is obvious actually if you think about it. And to have a model, I mean, the CSM2 also has daily data, but then it would take ages to train that model. We have not done it so right now. So our model basically is the results do not change much even if we remove tau x, tau I. So our prediction skill is essentially coming from the subsurface layers, which, yeah, which makes sense. I mean, the subsurface ocean dynamics is even slower than the surface dynamics, right? And then maybe some kind of memory in the subsurface dynamics is being exploited here. Yeah, we have not looked that deep into the ensemble members, to be honest. Yeah, but maybe it could be possible. I mean, there's nothing to say that this is not possible. Yeah. Yes. Additional prediction. What do you mean by additional prediction? I mean, we do this one-shot prediction of these 2 years, 24 months, 28 months actually. And because you already begin to, if you look at this plot, you already begin to lose skill of prediction around 19, 20 months. So then we don't bother for repeating this. Yeah. I mean, 24, 28 months already means that you have prediction like for more than 2 years. Yeah. Okay, to summarize, I mean, what I want you to take home is that ENSO is a high impact, non-trivial spatiotemporal modeling challenge. Okay. And deep learning ENSO models have shown to be high performing for up to around 2 years, 17, 18 months, or actually 1.5 years to 2 years. And even though like in this whole field started like only 5 years ago in 2019, they have made quite some progress. But then what we sort of try to improve upon is that current DL ENSO models are deterministic and scale poorly and lack generalizable representations. And our model, we contend, our model is well calibrated, it scales well, and it also produces an ensemble. And these things are also related. Right, okay, that's basically it. I'm also looking for a postdoc in my group if somebody's interested, or if you know somebody who's looking for a postdoc position, just let them know, write to me. Right, great, thank you.
Have you looked into different flavors of ENSO?
As of now, not. So I have Jakob, another student of mine who's actually graduated. So he developed what we call a hybrid model that basically, where is that? That basically takes this CDC limb, the limb model, and trains a LSTM model on the residuals of the limb model. And in that project, we looked at like, because limb is a linear model and it still has actually fairly decent skill for up to a year or so. And then if it has decent skill up to a year, so it's essentially, you're saying that linear dynamics does well, but then we train a LSTM on the residuals, and then of course skill improves a lot. And then we have this whole, digging deeper into, where do the nonlinearities matter? And it turns out that the West Pacific is very crucial in this. Limb does not perform well in the West Pacific, and the LSTM sort of adds predictability in that region specifically. And in that sense, in that project, we also looked at the different flavors of ENSO. But in this project, as of now, we have not looked at like EPCP, we have not looked at this. No. Yes. Yeah. No. Yeah, because it's more computational effort. I mean, we are already at comparable. So our goal is not really to sort of come up with the best ENSO model, or we're interested in a few other things, like we want scalability, we want calibratedness, and so on. And for us, like we were doing slightly better than Geoformer, which is the state of the art. So we were like, let's not waste time fine tuning, because fine tuning can be like again a rabbit hole. You can spend months in fine tuning, and we felt like let's just write up this paper and yeah. Oh yeah. Thanks.